Hi everyone, I'm Andrew Wakefield. I'm a project engineer at Northumbrian Water. At the time of this case study delivery, I was a water quality scientist for the company. And just for people who might not be aware, Northumbrian Water is the main water and wastewater service provider in the northeast of England. I'll let Peter introduce himself.
Yeah, afternoon, everyone. My name is Peter Bell. I'm a project engineer within Northumbrian Water, so I work with Andy and the engineering team. At the time of this project that we'll cover, I was the team manager / site manager of Mosswood Water Treatment Works. So I was heavily involved in the install works, which we'll cover a little bit later on.
Yeah, cheers, Peter. So just the contents of the presentation. So we're going to go through the investment journey at Mosswood Water Treatment Works. We're going to touch on the use of UV for disinfecting water, the solution development that took place, looking at a few of the different options that we considered, then focusing on the preferred solution and design considerations, the installation and delivery of that solution, and then the asset in use and lessons learned. So just to give you a bit of background, Mosswood Water Treatment Works is one of our biggest drinking water treatment works at Northumbrian Water. The site is situated on the border of Northumberland and County Durham, and it lies within the North Pennines area of outstanding natural beauty. The raw water source for the site is the Derwent Reservoir, which has a capacity of 50,000 million litres and was constructed in the 1960s. The works can also be fully supplemented with an alternative raw water supply, which is from the River Tyne, and this is through a pumped arrangement, which is part of our Kielder transfer system. The Kielder transfer system allows us to move water from the much larger Kielder Reservoir up in Northumberland around much of the northeast. It's particularly vital for maintaining flows to the Tyne, the Wear, and the Tees rivers. And we also have the availability to supplement some of our water treatment works with that source. The reservoir catchment for the Derwent is mostly rural and sheep grazing. It's approximately 100 kilometres squared, but the river pumping station catchment is significantly larger with multiple land uses throughout. So just going into Mosswood Water Treatment Works itself. So the works was built around a similar time to the reservoir, so in the 1960s. And the treatment process at the time was fairly conventional, but it has had several additions over the years. The current treatment process is the addition of coagulant and flocculant to aid the clarification process and sedimentation through 27 clarifier units. Clarified water then proceeds through rapid gravity filtration, of which there are 12 rapid gravity filter units. And then disinfection is with chlorine and the addition of UV, which we'll talk on throughout the presentation. The site has a maximum output of 152 million litres per day, but it typically produces around 130 million litres per day. And there are two main supply outlets. So there's a pumped supply, which feeds large areas of Durham, and a gravitational supply, which feeds areas of Sunderland and South Tyneside. The work supplies approximately 880,000 population, and it's a critical supply for a lot of our customers. So minimum downtime can be afforded before customers start to lose supply. So just going on to the investment journey and where sort of this project, the concept came from. So in 2016, there was increasing concern within Northumbrian Water around the quantity and quality of water feeding the work. So that's from both the Derwent Reservoir and from the River Tyne. We were seeing increased variability in the impound and reservoir levels, and long term, the reservoir level was on a decreasing trend. We were seeing more extreme and variable weather, which was attributable to some of the climate change conversation taking place. And some of the deterioration we were experiencing was microbiological and chemical challenges. Because of the variability in the reservoir levels, we were relying more heavily on the River Tyne supplementation. so bringing water from the pumping station into the works directly. The River Tyne, being a river source rather than an impounding reservoir source, represents a more significant raw water quality challenge for the works. And the main concern was around cryptosporidium. So cryptosporidium, what is it? Well, it's an intestinal parasite and it infects a variety of animals, including humans, cattle, sheep, rodents, cats, dogs, but also birds, fish, and reptiles. So there's a wide variety of species. Cryptosporidium oocysts are approximately 5 micron in size. They have a very high survival rate in the environment and water. They can survive for months in moist soil or water and survive the harsh environmental conditions, so both hot and cold environments for extended periods of time. They're also extremely resistant to chlorine, which is one of the big challenges around drinking water treatment and disinfection of these parasites. Transmission is by ingestion of infectious oocysts, and this is typically through direct contact with infected persons or animals, or through consumption of contaminated water and food. The resultant illness from consumption of this is cryptosporidiosis, which leads to symptoms of diarrhea, sickness, and dehydration. In healthy humans, this is just particularly uncomfortable, but in immunosuppressed individuals and infants, it can be life-threatening. So changes in raw water quality and this increase in risk from cryptosporidium, what did it mean for the site? So at Mosswood and Northumbrian Water in general, we carry out annual assessments and have site-specific disinfection assessments and policies in place, which summarizes the disinfection needs and risks posed by the raw water and the treatment requirements. So evidence was indicating a deteriorating trend, and this was confirmed by a change in classification on the site around the Derwent Reservoir water for cryptosporidium, so the parasitic protozoa. It changed in 2017 from a medium risk to a high risk, and therefore the treatment requirements to ensure safe drinking water was increased essentially. So we needed to invest in the works and ensure treatment was sufficient. The SSDA ensures a formal process within the company, and it's fairly consistent as like an industry approach, but it essentially allowed us to make the case within the company for the need for treatment enhancement to ensure effective disinfection in the future. So in 2017, a project was launched to investigate the additional treatment stages to target crypto and essentially mitigate any future risk. And this involved initially a stage of solution optioneering. So conventionally, crypto is removed through physical treatment, so filtration, coagulation, and sedimentation. We looked at several options around this. So adding an additional filtration stage or modifying the existing filtration stages. So to do this, we looked at potentially adding an additional filter to the process, so a granular activated carbon plant. But this was ruled out due to the high levels of cost associated with doing so. The project would require the purchasing of land. It would alter the hydraulics of the site. So the raw reservoir gravitates into the works, and the majority of the treatment is through gravitational flow, with the Durham system only being pumped into supply. If we were to do this, it would completely change the hydraulics of the site, and there would be a lot more interstage pumping and the associated costs and energy consumption with that. There would also be increases in carbon, particularly through the construction of the additional stage. So we started looking at alternative solutions, and UV disinfection was brought into the conversation at that time. So UV at the time, it's not particularly a new technology. It's been well used within the industry in both water and wastewater applications. And we knew at the time it can be used to target crypto specifically for disinfection. So two main options were developed based on the known technologies at the time. Option A was to install a large UV treatment plant between the rapid gravity filter stage and the final treated water tanks. And option B was to install two UV treatment stages, one on each of the works outlets. Before getting on to the options themselves, I thought I'd just touch on UV and the disinfection provided by UV, just in case anyone's not aware. So what is UV disinfection? So it's essentially using the ultraviolet range of the electromagnetic radiation spectrum, so particularly wavelengths between 200 and 300 nanometers. These wavelengths are germicidal, which means essentially they damage microbial cell components such as DNA and RNA, and that prevents cell replication and function, rendering pathogens harmless. Essentially, the UV radiation can kill the cells. UV, one of the issues is that it does not impart a residual within the water itself, so it's a contact time process. So UV dose is the effective application of UV to a cell, and this is measured by the intensity of the UV and the dose contact time. We typically use UV reactors containing UV lamps to produce the UV radiation, and typically the way it's installed is either having the water flow through the reactor or the reactor lamps placed in a channel or something along those lines. So we were developing our disinfection strategy around this time to ensure that future mitigation of any further deterioration was in place. And we essentially decided to use a multi-stage approach to disinfection at the site. So we categorize disinfection requirements based on the different pathogen types. So we look at bacteria, viruses, and protozoa. And chlorination is very effective at disinfecting bacteria and viruses. So that both are fairly sensitive to chlorination, and you don't need significant levels of chlorine application to essentially render viruses and bacteria harmless. So the chlorination process on site would remain in place and be sufficient for bacteria and virus disinfection. The main concern was around this additional risk associated with cryptosporidium. So we already had physical treatment on site, which was accounting for a proportion of removal and at that time sufficient. But the recognition was that the crypto levels were increasing, and on the increasing trend, at some point we would need this additional disinfection. So chlorination is essentially ineffective for cryptosporidium, as discussed before. So thankfully, UV treatment is very effective. Crypto is very sensitive to UV light, and you need relatively low UV dosage to effectively kill or render inactive the cryptosporidium cells. So we needed to quantify what level of UV was required to future-proof the works, and we settled on a 2-log removal. So this is essentially a 99% inactivation. And to achieve that, you only require a 5.8 millijoules per centimeter squared UV dose, which is relatively low when you compare that to what would be required for virus inactivation at 2-log removal. You would require 100 millijoules per centimeter squared for the same sort of inactivation of viruses. So it shows the difference there in how effective the UV dose is. So back to the options. So option A, UV treatment between the RGFs and the contact tanks. This would be 2 large reactors capable of each producing the required UV dose, but at both of them would have to be able to produce the UV dose at the maximum site output, which is 152 million liters per day. So you're looking at very large scale UV reactors, very energy intensive, and the reactors would need to be able to do full flow immediately with minimum downtime. The buildability and commissioning would have been very complex with a solution of this type. It would require new buildings on site, pipework reconfiguration, and total change to the hydraulics of the site. And we would also live with a considerable risk during maintenance of one of the reactors, as essentially the actor would act as a duty in a standby system. There would be significant consequence for catastrophic failure as well on final water quality. Option B was the UV treatment on the outlet mains. So this would be two separate systems on each outlet main. Again, you would still need large reactors, looking at around 80 megs on each side. Similar sort of very high energy consumption costs, need to procure land, new configuration of hydraulic arrangements of the site. You would also need uninterruptible power supply and backup generation. So at the time, based on the technology available to us, the option B was the preferred solution. It had lower risk associated with it compared to option A, and we applied for Ofwat enhancement funding for AMP7. This received support from the Drinking Water Inspectorate, who are the UK water regulators, water quality regulators, and they essentially issued a legal notice, which meant that we were committed under the water quality regs to essentially deliver a solution that mitigated future risk at the site. The estimated cost for this option was around 7.1 million at the time. Unfortunately, in 2019, an alternative option was identified. We were introduced to a new UV technology which was coming onto the market, which was the wafer UV reactor, which was by ATG UV Technology, who were subsequently acquired by Evoqua, who are now part of the CIWEM group. This allowed us to revisit the solution development, and what we essentially looked at was putting these much smaller UV reactors on the outlets of the rapid gravity filters for a more favorable solution compared to the options A and B, which have just been discussed. So this is the wafer UV reactor. It has an extremely small footprint, as you can see. All of the dimensions are less than a meter. The manufacturer at the time provided details around its operating ranges. So it was able to do 0 to 40 MLD, which was suitable for individual RGF flow rates. They contain 6 UV lamps of medium pressure and contain a mercury amalgam vapor. They would have quartz sleeves, so the 6 UV lamps would be contained within quartz sleeves, and they provided several benefits in that there was physical protection to the lamps. It would protect around fouling, and those quartz sleeves could be replaced as part of servicing. And it also reduced the risk of nitrate to nitrite formation, which is a disinfection byproduct consideration around UV. The proposal would also allow us to install UV upstream of chlorination, mitigating the risk around disinfection byproducts associated with having chlorine within the water at the time of UV application. There was several risks with taking this UV reactor on at the time, and that was around the validation. So there's a requirement in the UK water quality regs that UV reactors used for disinfection must be validated through an appropriate body, so a European or a US EPA standard. So we took this risk on at the time because it wasn't validated, but through the project, the contractor did get US EPA validation confirmed, and it essentially proved that the reactor would be suitable for all of the operational conditions it would come under. So just looking at it in a little bit more detail, essentially we're looking at installing the UV reactors on the outlet pipework of each rapid gravity filter. This would mean that we would have 12 individual reactors, one on each of the individual filters, each capable of doing the filter flow rates are sort of in the range of 0 to 20 MLD. It would be suitable for the fact that the filters were the last physical treatment process on site. So the water quality being presented for disinfection by the UV reactors is already suitable, so meeting the water quality regulations in terms of preparation of drinking water before disinfection is applied. And there was a lot of positives for the this proposed design at this stage compared to the other options. So it was essentially much lower in overall cost. The potential buildability concerns within the existing assets were much more favourable than having to construct an entirely new treatment stage or procure additional land. The reactors were also lower energy costs associated with them, although we did need to consider power arrangements for the site, which Peter will touch on later. It would minimize impact on the site during project delivery, so we're able to commission and get the asset in use with minimal impact on site output. And essentially, this system could be fully automated and integrated into the operational control and the filter backwashing process. I'll now pass on to Peter, who's going to touch on the project delivery aspects. And Peter, if you'll do your best Chris Whitty impression when you need the next slide.
Yeah, next slide, please. Thanks, Andy. Yeah, so just to cover off how we actually went around the install for this. So for all, the wafer unit is very, very small in its footprint. We also found that the space that we were going to put in was very small, which you can see in the bottom right-hand picture where we've took some pipework out. As Andy mentioned, the site was built in 1960s, and we hadn't actually sort of done any major intrusive or changes to this pipework arrangement from those times. So we had quite a bit of open space to play with, but the sheer amount of equipment that we actually had to fit in was quite substantial. At the time, we identified that Filter 9 was a really good opportunity to get in and actually do a trial of this equipment and validate all of our thoughts that we went through the design process. Filter 9 was out of service at the time for a media change, which is a routine task that we go through every so often, depending on the filter media life cycle. So it presented a good opportunity to trial this without causing any further impact to the site. So the first question to ask ourselves is, can we actually get the reactor to fit within the dry well? And with that come a lot of challenges with the pipework. So we had to configure the pipework in such a way that it would actually introduce some hydraulic losses. So we need to understand what those hydraulic losses were likely to do to the site flow. Were they going to majorly affect it? What would that look like? One being introduced to then 12 of these being introduced. We then had to consider around that pipework support. So the concrete that was holding the pipework, does that have the right amount of strength? Is the floor strength suitable? There was no thrust blocks in, but we need to put thrust blocks in, pipe supports, all those different types of things. The actual filter outlet channel, which you can see in the top picture, that is the filter outlet channel sort of soffit. Underneath there flows 130 meg of water on average. It's about 1.6 meters deep underneath there. It's an enclosed channel, but we had to bring a lot of equipment across the top of there, which we had to understand was that channel capable of taking the weight of the equipment used to install it. So we had to do a lot of concrete tests on there to make sure that we understood the integrity of it, to make sure that it was safe to take this load. The loads were up to around 700 kilos in weight. Some of the most of that was through a bespokely made manually operated crane unit that was portable, that we got bespokely made for it. And what that allowed us to do was to lower the equipment down into the dry well safely without the need for major sort of block and tackles being attached to the ceiling above us, when we could then move that around quite easily. And the benefit of that as well is that we were able to then leave that on site for any works that need picked up in the future around it. The other key challenge as well is actually fitting this into the pipework whilst maintaining the site operation. So the top pipework that you can see where it has the teal coloured additions, the teal, red and blue valves added, that is actually the filter backwash main for the site. The way the filter backwashing works is it's on a large ring main fed from a header tank. And it is cross-connected at the sort of top end of the ring main. But what we found was that if we were to supply filter washing on the even numbers, so that the odd numbers run down one side of the channel, which you can see sort of to the top left-hand corner of the first picture. The other side of that channel is the is even numbers. So we had to make sure that we weren't going the long way around that channel. What we found when we were going the long way around the channel is there was a lot of hydraulic losses introduced due to sort of a pipe bridge at the bottom. And that reduced the flow down to 350 litres a second, which wasn't suitable for the backwash that we needed and introduced too much of a water quality risk. So we had to work out how we would then maintain this backwash capability whilst we didn't have the ring main available. Now on this one specifically for number 9, because of the amount of filters, it only actually affected filter number 11. So it was much easier to manage that filter because we could stagger the filter washes, which are approximately every 4 to 6 hours per filter. We could stagger it, but I'll touch on later on how when we started to get down to the lower number filters, so the likes of 1, 2, 3, and 4, we really struggled with the impact of the filter washing a lot further upstream. So yeah, we commenced this in 2019. We went through the constructability trial, found it to be really successful, which then paved the way to proceed with the project. We validated all our thoughts, and then we went on to the remaining 11 filters. Typically, just as we were about to get going, the COVID hit the country, and this significantly affected our supply chain, and obviously, the whole country as we know it and the world. But what we found a lot of challenges is obviously material shortages, labour shortages, and difficulties around that. A lot of our supply chain were travelling from various places around the country, and obviously there was restrictions in place on that. We also found the most difficult challenge was actually the teams that were working on this equipment were from various different framework partners. And because of the sort of the bubble setup that we had at the time, where various teams could work at the time, we weren't able to work in a sort of concurrent fashion. So we had to have sort of mechanical teams go in and then them leave the space, then electrical teams go in. So we couldn't have the teams working alongside each other, really reducing the installation time. So that was a real challenge. Not to mention the fact that we were working in a confined space, which obviously wasn't great for COVID. The other key consideration that we had to have around COVID was our site staff as well. So obviously being a critical water treatment works, we had to be very considerate of how we protected the site staff and didn't put them at risk. So we done all of the segregation, separate working areas, all those different types of things, but it was a real key factor that our site staff were doing a great job in sort of isolating themselves where they could, and reducing that risk of spreading coronavirus. But it was a real key concern for us that our operational staff could have been affected by the amount of work going on site. So that was a real challenge, and we had to slow things down and pick things up as as the guidance sort of allowed us to do that. But it was a real challenge that we had. With Mosswood being a critical water treatment works, we had to maintain the operation of the site. So we had to have a flexible program due to the criticality of the site. So sometimes when we mark things up to go in and get working on that, we were unable to do it, just purely because of other network considerations. We might have had other demands to deal with. Sometimes windows presented themselves earlier. We could get in there. It was a little bit flexible on that. The other consideration that we had to have around that was during summer 2020, when people were allowed back into socializing and within the gardens, etc., we've seen an absolutely huge demand for water, linked to barbecues, garden parties, etc., all which sort of massively spiked it. So it was a real challenge we had to maintain the output at Mosswood, strategically find these slots in the demand profiles and get in and get that bit of work done. So the way we done that was we agreed a 2-week outage with the teams, with our network teams, and that was to reduce the works by about 14 megalitres per day. Now, just to give some context, 14 megalitres per day is actually bigger than some water treatment works outputs within our region. So it gives you sort of an idea of the amount of sort of water that Mosswood's able to supply. The next challenge was around, say, managing how we got in and done this work. So we had a 24-hour window to get the sort of critical pipework installed, which is this top pipework that you can see in the top right-hand corner. That's the backwash main, what you can see there. As I mentioned earlier, when we done filter 9, getting into filter 11 not washing filter 11 was a fairly straightforward task because we could stagger the filter washes to do that. But when we started to get down into the lower numbers, like say the 1s and 2s, the way that the ring main affected things was that meant when we broke into that pipework and made those isolations, we weren't able to wash the upstream filters of that on that specific leg because the water wasn't able to flow there, and we didn't want to go the long way around. So what we had to do is we had to line up that piece of work for a good 3-4 days prior, slowly changing the filter wash sequencing. Not so much that it impacted the site, but enough that we built up a window so that we had sort of a 24-hour slot to get in there, do the pipe work, remake the pipe work, and then allow the filter washing sequence to continue. Just to give some context, if we weren't to wash the filters after the running period, which is around 48 to 60 hours, depending on what the water quality profiles are like at the time, you then start to see turbidity breakthrough or loss of flow through the filter. So you would start to impact the site water qualities and quantity. On a few occasions, we did find that when we were sort of going into some of this pipe work, we found the isolations quite difficult. We found some valves were passing, and that made it quite difficult for the site team. So we had to then sort of agilely work around that. What we then ended up doing, once we realised that actually it was of much more benefit to the program to get in there and proactively replace those valves. Originally, it wasn't in scope to replace some further upstream isolations, etc. But we then went in there and proactively changed them, which was of much benefit to the program. And just to give you a flavour of sort of the pipework installation from what it looked like from the start. The top picture shows all of the pipework dismantled and ready to get into there, and then the bottom picture shows what it looks like when it's complete. You can see the UV reactor unit in the silver case and just down at the bottom of the screen there. Teams worked for about 24 hours on that to get that in that position. It was 2 teams of some specialist contractors who were absolutely brilliant. They come in and they worked overnight to split the teams up and worked overnight to get it into that position, which is quite a feat considering how tight it is and how many actual pieces of pipework to get in there. Alongside that as well, as part of this program, we also launched the power upgrade works to fulfill the UV potential. So when we initially installed the UV, we recognised, well, as part of the design, we recognised that we wouldn't actually be able to run the UV reactors at the full power if we needed to. Just to give a bit of context, they on average run around 25 kilowatts. They can go up to 50 kilowatts. So we then proceeded with a project to upgrade the works power. That involved a new main supply from our electricity network and also the installation of a new site generator, which was then able to power all of the UV at 100% as well. So quite a substantial power program launched alongside this as well, which, we use the same supply partners, framework partners. So we got a lot of benefits from that. We reduced the overheads around that. Those teams were able to drop on other pieces of work within the projects as and when them opportunities allowed. Next slide, please, Andy. So just to give you a little bit of overview of what else went on as well. So it wasn't just the mechanical and electrical installation works that went with this. We also had to do quite a range of system integration into our SCADA system. So for those that don't know, SCADA stands for Supervisory Control and Data Acquisition System. So that is how we effectively run the water treatment works from computers to then be able to operate the site in a remote fashion. So the operator is able to, from a central control room on the site or various other client units around the site, able to operate various parts of the plant, able to delve into the details, look at trends, etc., and overall run the plant. So we had to integrate that into the site. So we started to build up what those mimics might look like. So this is a SCADA mimic of the filter. So it shows the process of filter number 7. We then had to build in the UV reactor, which you can see is indicating as running within the pipeline. We had analyzers put into there. We had to reprofile the pipework, etc. So we tried to make that look in a line diagram as close as what we could to the actual physical install. But with this come quite a task in itself as well. That isn't just a case of drawing that up and loading that in. You also have a lot of rules, inhibits, alarms, functions, etc., all built into SCADA so that it gives that overview. And just to show the level of detail of what this started to look like, what we loaded into, we've got a couple of slides to touch on that. So Andy, could you just flip the next slide, please? So this is some of the alarms associated with just one filter and the level of detail that we can see. So you can on the left hand side, you can see that we've got flow rate, chamber temperature, UV dose set point, UV dose, UV transmittance, all stuff that is absolutely critical to understand the operation. We then drop down into the system power level, what it's running at, the indication of the log removal, and then what the status is looking like. And then on the right hand side, you can see some of the alarms that go with it. So in total, there was around 30 alarms, not just the ones that you can see on the screen, but there was about 30 different critical alarms in there that we had to do end-to-end testing on. Obviously, we've done end-to-end testing on all these, but the critical ones, we made them show it in an easier fashion for the operators to go in there and be able to see what the fault was, give a lot more information around that. So in total, you imagine this amount of data being replicated 12 times, absolutely huge amount of data to process within our system as well, and build that into our alarm banks. Next slide, please, Andy. Because of the level of information available, what we then done is we then broke that down to the absolutely critical points to help the operators understand the performance of the UV. So just to give you a little bit of an overview, the first column here is turbidity. So that is showing what the turbidity of the filter is coming at. So Andy touched a little bit on this earlier, but we need the filters to be presenting less than 1 NTU turbidity so that disinfection can take place appropriately. UV transmittivity is another key parameter. So if it is less than 70%, we can't target all of the areas that we need to target. The transmittivity won't allow that UV light to pass through and target all of that cryptosporidium. So that was another key parameter that we tracked. The UV dose shows that we are meeting the minimum dose. So, as we touched on earlier, we need quite a small amount of dose of 5.8 millijoules per centimeter squared. When we run that 50%, we're achieving well above that. So it goes to show that we've got the right amount of dose there. The analyzers for measuring UVT, they need to have a representative sample to that. So we monitored the flow status to that. We then went on to show the power, log removal, and the flow through the filter as well, and if the valve is open. And then what we've done is we created some rules around that to say if all of these parameters that are running, that are in green, are running as they should be, then the system was in validation. And then finally on the bottom right hand corner is the full system invalidation is yes. Now, if the approach we went with to sort of simplify our operational understanding and how we reacted to it. If one filter fell out of validation, then the whole system would fail, and we were unable to accurately see where that potential cryptosporidium had come from. So we basically based it on the whole system must be in validation to prove that its worthiness across the plant. Give you a little bit of indication of some of the operational parameters that might be useful as well. So that UV reactor power, we set that as a minimum to run at 50%, but what we could do with this is we can see if the UV reactor power is climbing. We can say that we maintain our minimum dose, the UV reactor is climbing. We can then start to delve into why is that starting to climb. So that could be because the quartz sleeve are fouling. So we could get indication that the wiper isn't doing its job that it's meant to be doing. It could be an indication that the transmittivity of the water is reducing. eventually we would get to a point where the power would get to 100%, and then the dose would continue to drop. After a certain while, the system would drop out of validation. So all of that data helps us understand what the performance is looking like and take preventative measures to stop that from happening. So really, really useful. But just to give a bit of context, obviously the amount of alarms from there is a huge amount of data to process. Next slide, please, Andy. So yeah, we've got a little bit of flavour of the SCADA overview, but then the next sort of steps is, once we went through that commission, is then how we integrate this process into the business as a whole. So the first key challenge really was that it's the first of its type within the business. So we have UV on some of our other sites, both water and wastewater, but we've never seen this wafer type technology before. And the UV reactors that we've got on some of our groundwater sites, it's probably fair to say that they're not as at the advanced level of sort of information available as what they are here. So they simply don't need to be. They can do what they need to do with much less amount of information sort of being processed. But for this application, we needed to go to this level of detail. So it was absolutely huge change. And not only that, what we were doing as well is introducing a whole new treatment process. So our operational teams were really well versed with the plan from start to finish. But actually, we were introducing a whole new treatment process to Mosswood. So we went through quite a lot of work on how we sort of educate the business, educate our site staff on doing that. So we've done a lot of theoretical training, which was delivered by our NWL technical specialists. So that was going into the detail what Andy touched on about how UV works, what it targets, what it doesn't, the reasons for it, etc. And then we started to delve into the practical training. So we delivered practical training to both ops and maintenance, so that the operations team knew what they needed to do on a day-to-day basis in terms of validating, calibrating, looking after all of the different bits of equipment, how to do sort of routine diagnosis, fault finding, whatever it may be, resets, anything that was needed, all the way to the more extreme stuff with maintenance, where they might do major intrusive works to find faults or to do servicing, lamp changes, whatever would be needed. The approach we took on this was we actually, for maintenance, we brought in Evotwa, who were the manufacturers of the equipment, and we done some service and works alongside them and broke into the system, done that intrusive works, which really helped to build maintenance's knowledge of the system. So we weren't just solely relying on the manufacturer. Obviously, if something went wrong out of hours and we needed maintenance support on this, our technicians had already been in, they knew what the equipment looked like inside, they knew the dismantling methods, etc. So it was really valuable to do that. The next part to think about was, away from all of this theoretical stuff, we actually introduced a huge amount of assets into our asset base. So we introduced 96 major assets, so 36 actuated valves, 24 UVT monitors, which you can see in the rear Realtek units, 12 UV reactors, 12 control panels, 12 sample pumps in line. All of them need the routine sort of preventive maintenance on it, any reactive work, all a part of that upkeep throughout their life cycle. The other bits that we had to introduce as well, getting this into the business, was the creation of standard operating procedures to assist the team with all of this. So so that they had something to refer back to. We went through all the training, but obviously people need that sort of paper to refer back to as and when they need it. So we created a lot of them, brought them into the business as well. We also touched on within there about the escalation side of things. So how we might escalate things out of hours if we found to be issues with it, what the operations team need to do, what maintenance need to do. And that then rolled on to actually training some of our support teams as well. So not just in terms of operations and maintenance, we then went on to train our water quality teams who would support the site with any water quality issues out of hours. This training rolled quite wide throughout the business to build that understanding. Next slide, please, Andy. So it's been in service now for probably touching on 2 years now, and we've found it to be a really great product, a great project overall. But undoubtedly, we've learned a lot of lessons along the way as well. So when we have been servicing the UV reactors as part of the routine maintenance, we did initially find it quite challenging. So the picture you can see on the top is filters 1 and 2, where these ones are actually smaller than the rest of the dry wells, so it was really difficult. We had to change the design slightly to get into these, but what we found was that actually when we put the open mesh flooring in, which you can see there, we had to make that in such a way that it could be dismantled quite easily through quick fixings, etc., to be then dismantled to get down onto the UV reactor and allow someone to work in there. So that was a real challenge, and to be fair, it remains a challenge to this day. The space that we're working in. Thankfully, it's not, it isn't a daily activity. This is something that's once every 6 months. But this picture does just gives you a flavour of sort of that challenge. Our links with Evotwa have really come on like leaps and bounds. We've got a really strong relationship with them now. At first, we found that we were struggling to get the scheduling right. For both our parties, we were finding we couldn't quite get the service and absolutely near it. We were doing it, but we were seeing overruns on what we estimate at the time might be. We were struggling with methods of isolation, etc. But we've worked through that, now developed a really sort of lean and quick methods of doing things, preparing the filters to be serviced, slotting those into our network timetable, etc. We've really made that process quite slick. The equipment has proven to be really robust and reliable as well, which is massively helped. So we haven't seen any major defects at all. We've had the odd sort of routine servicing and minor faults, but absolutely nothing in the way of major defects, which goes to show how good this equipment is. The understanding in the business is growing and continues to grow. So both from a treatment perspective, so our operational teams are becoming more and more comfortable with it. When we first started, there was varying levels of understanding through our operational team. All had a good base level of understanding, but we found that other people, it was quite sort of developed their knowledge. Other people were still sort of uncertain around it. Now that this has been in place, we've got really strong understanding of that. The operation of the equipment, people are really confident going in, altering settings if we need to fine tune against water quality, etc. So we're doing really well with that. And what we've also found is that our wider support teams, their knowledge is really grown as well. So our water quality support teams or out of hours operational teams, etc., they have that understanding as well. So that's really heading in the right direction. The other sort of thing that we are using this project as is a really good reference point of we took an innovative product that carried some risks and delivered it, and we're getting great benefits out of it now. So it's a great showcase for us internally for projects on what's possible by taking on innovation, which we all know can sometimes come with some risks. And we've also shown how we can develop really complex new assets being retrofitted onto old assets, which isn't always easy. We've also been able to standardize the approach and share learnings with the UV installs at Lumley. So we've replicated this process at Lumley Water Treatment Works. And we've now got a sort of blueprint that we can then roll out across all of our sites and repeat this. And most importantly, I think to touch on is we've had absolutely zero cryptosporidium failures. So I guess really is testament to how good the project's been and how well the product's working for us. Next slide, please, Andy. So just to give a bit of a summary for everyone, we covered the investment journey at Mosswood, where it all began, where we come from, how UV actually works, where we went from our initial solutions all the way to the wafer units on the end of the RGFs, the challenges we faced during the installation and the delivery, now what we're seeing that the assets are in use, and a couple of lessons learned. But overall, I think that's pretty much it. Thank you very much. Mike, I'll hand over to yourself.
Thank you very much. I'll start off by saying thank you for your presentations. We've got about 5, maybe 6 minutes left, so I'll try and we've got a couple of questions coming in just before, in case anybody else has any more questions coming in. A couple of key points for me for that is how difficult the challenge is to keep the site operational. Plus also the stuff about, you mentioned during COVID, unseasonal demand, and not just keep the site running, but actually keep it running at its maximum capacity for such a long time while trying to deliver a program. And also the training and upskilling of the staff. It's not just the site team, but actually it's all the support staff as well, which by the sounds of it was a huge challenge. Yeah, thank you for sharing your case study with us. So there's a couple of questions coming in. We'll probably do them in order they were received, if that's all right. So the first one is from Ian Luckman. He's asked, were you able to find out why the raw water deteriorated around 2017? Or was it to do with a different method of assessing the risk? I don't know, maybe Andy, if you want to answer that one.
Yeah. So we did do catchment investigation at the time, so collaboration with landowners and farmers in the reservoir catchment, because it was much more manageable compared to the river catchment. But essentially we couldn't identify like a specific source or a change, so no sort of changes in farming practice or anything like that, leading to this increase in source of crypto. But what we were seeing is the change in reservoir levels and the variability of the weather conditions in that area. So what we essentially attributed it to was essentially that climate change sort of element. So as the reservoir levels are decreasing, and then we're seeing these like very heavy downpours and rainfall and rapid refills, essentially that could quickly sort of wash crypto into the reservoir itself. We're also having to pull from different heights in the reservoir for the raw source, so taken from lower water sources within the reservoir, which could have disturbed essentially like sediment that had cryptosporidium in place. So essentially didn't get a specific source, but attributed it to the sort of change in weather conditions and the variability of the reservoir levels.
Great, thank you. Hopefully that answers your question. I'll move on to the next one, if that's all right, from James Littler. What impact would lamp breakage or mercury release have? Do you have space to catch it and just lose one filter, or would you have to lose the whole site?
Yeah, I can pick this one up. So lamp breakage and mercury release was considered as part of the design. So one of the things we did employ, which we didn't touch on in much detail, but was fail-safe measures around the installation. So on the critical and fatal alarms Peter mentioned, they would fail-safe the individual RGFs out of supply. So the outlet valve would close and essentially take that filter offline, preventing any sort of contaminated water passing into supply. One of those fatal alarms was around lamp breakage and earth leakage faults, which is one of the ways in which it would represent itself to the system. Another sort of mitigation we put in place was the servicing contract. So we would replace the lamps well before their recommended run time, so they were replaced annually. And then the quartz sleeve provides a level of containment for the lamp, so any breakage within the lamp itself may be contained within the quartz sleeve, which would minimize how much would be released. A single RGF being offline would obviously be minimal impact on the overall site output. And then finally, just I guess the most risky period for lamp breakage would be during manual handling and servicing itself, rather than when it was in supply. With it being final filtered water, you're not seeing any sort of solids coming through the process, so we wouldn't expect to see any sort of breakage through collision or anything like that with the water flowing through. Hopefully that answers it.
Great, thank you. We've got a couple more questions and hopefully a minute to try and get them in on time. Another one from Ian Luckman. With only a single UV contactor on the outlet of each RGF, how do you manage outage or maintenance with no standby? Is UV operating all year round?
Yeah, I'll cover that one. So yeah, the UV operates all year round, 24/7. What we do when we need to get in there and service it is we essentially just take that filter out of service for the day. We just agreed to reduce the site outputs with our network teams. We get in there and get that service and get it back online, and we can complete that within 8 hours now. Like I say, we've really worked alongside Evotwa, the contractors, to nail that process now, and we're delivering that time and time again.
Great, thank you. Another one from James. How did the CapEx costs compare for the 12 small reactors that were installed versus the original plan, which was 2 large reactors?
Yeah,
I can pick this one up. Yeah. So the sort of original project budget was proposed around option B. So we'd allocated like a large amount of money. We were able to deliver both the Mosswood and Lumley solutions with that original budget. And I think actually it came in under that budget. So overall CapEx costs were significantly lower with the 12 small reactors, mainly due to like not needing to do significant civils and pumping arrangements and reconfigurations of the site. We're able to fit them into the existing assets.
I've got the figures to hand on this one. So Mosswood was 7.1, but it came in at 3.1 million. And Lumley was 2.5 million, and that came in at 1.5 million. So let's see, actually coming near enough half.
That's some big figures there, some good figures, isn't it? There's only one more question to answer, so if you're happy to hang on, let's finish that one off. This one's from an anonymous person, but noticed that the images of the entry and exit from the reactor was followed by some quite abrupt bends. So they've asked what was the results of the CFD validation report, essentially.
Yeah. So what we did as part of the validation is compare our hydraulic arrangement and design to the design for the validation that the reactor went under. So the arrangements on site had a 21% inefficiency when compared to the validation arrangements. So as part of the UV dose calculation, that inefficiency was built in. So on site, we knew that the arrangements were creating that inefficiency. So essentially the UV dose applied would be lower because of the hydraulic arrangements and turbulence through the reactor. So it was considered and factored into the design essentially, and then that was built into the online monitoring arrangements.
Great, thank you. So that's the last question. So just before we wrap up, I've got one final one from you. Quick yes or no answer. In hindsight, would you do it again, do you think? Obviously, there's a lot of benefits there, but would you do it again?
Yeah, we did it at Lumley, and there is potentially other applications we're looking at within the business for AMP8 to bring UV online. So yeah, we've sort of standardized this solution and are looking for other potential options at some of our other drinking water treatment works. Yeah,
great.
I think from a personal perspective as well, it's absolutely great project to be involved in. So it's here from the learning and understanding that we create in the business. It was great to be involved in.
Great, thank you very much. Couple minutes over there, but thank you all for your involvement. Thanks for preparing this. Thanks for sharing it. I think let's call it there then. So you should see a link come up in YouTube with the recording if anybody else wasn't able to make this. Thanks for your attendance. Thanks for joining, and thanks for our speakers. Let's pretend there's a virtual round of applause, but I'm applauding here. Thank you.
Cheers, Mike. Thanks, everyone.
Thanks a lot.
Cheers. Bye.